Okay, so in this introductory set of lectures to the Advanced Experimental Techniques Analysis course, I'm going to try and provide some of the common background to a lot of the experimental techniques that are used in modern physics. Now, none of this information is particularly focused in the individual experiment, although aspects of all of it are relevant to a number of different experiments. But it's going to give you that background theory to experimental techniques, the sort of information that as an experimental scientist, I really wish someone had gone and taught me rather than having to figure it out as I went along on the job. So an overview of what we're going to talk about in this series of videos, we're going to start off with the general description of the measurement process. We're going to talk about sensors, the bits that actually detect a physical property. We're going to talk a little bit about cables and why you should care about cables. Going to talk about sampling, which is making sure that your measurements you're doing are actually capturing the data. We'll talk about ways you can improve measurements and several of the strategies that are commonly used across lots of different types of experiments. So these are things like stroboscopic measurements, phase sensitive detection, null detection schemes, and pump probe measurements. And then go on to look at system control. So this is how you actually control the experimental system you're doing. We're then going to have another set of lectures after this, which then look specifically at spectroscopy techniques and also look at noise in experiments and what you can do about it. Okay, so let's start with the system view of an experiment. So nearly all experiments you're ever going to go and do end up with data being processed on a computer. And of course, computers are intrinsically deal in digital binary voltages, fixed voltage levels. So what we're really talking about is the process by which we go from some physical property that we're observing into digital voltage data. So we can break that down to a series of steps that have to be undergone. So first of all, we might want to think about the sensor. So the job of the sensor is to convert a physical property, so be it temperature, position, strain, pressure, magnetic field, light intensity, etc., into an electrical quantity. So typically that sort of electrical quantity might be a voltage or a current or a resistance, but it could also be a change in capacitance or inductance. But it's some form of electrical signaling. We then have to go and take those electrical signals. Very rarely are they voltages at the right sort of level that you can just feed straight into a computer. So usually what you have to go and do is do something to that electrical signal to produce a voltage that's proportional to the measured quantity and a voltage which is big enough that you can actually measure it with the computer. And also in signal conditioning, you include things that get rid of unwanted signals. So principally, of course, that's noise, but it can also be offsets and other artifacts in your signal. Part of the process of doing all of that, it relies on transferring signals from one part of your measurement system to the other part of the measurement system. And of course, that's where cabling comes in. The signal is transmitted through cables, and you have to understand what effect the cables have on the signals and the type of measurement you're trying to do. Once you've actually done the sensing and the signal conditioning and transferred the signal to the computer, you then have the process of turning it into digital data. So digitization takes a continuously varying voltage signal and turns it into a sequence of numbers. And again, you have to understand what's going on there in order to understand whether your measurement is giving a valid measurement of the thing you actually want to understand. The final stage of doing a measurement is the data processing. So manipulating the digital data to extract the parameters you're interested in. And we're not going to talk about that because, of course, that's very specific to each type of experiment you're doing. But of course, some of these sort of things you do in data processing are exactly what we were teaching in Computing 2 last year. So let's start with sensors then. So of course, it's not possible to go and give an extensive list of every possible type of sensor, but just to give you a range of an idea of some of the common ones, we're going to run through some of the things you might be trying to measure and different ways in which you're going to deal with them. So for example, if you're trying to measure a temperature, then depending on the temperature you're trying to measure, you might be using a pyrometer, you might be using a thermocouple, you might be using some metallic resistor, you might be using a diode, and then there are more complicated types of resistors that you use to measure temperatures in different circumstances. If what you're interested in measuring position, well then you're going to have some kind of maybe contact type of things, which might simply be a mechanical device, go into a potentiometer, it could be a piezoelectric type of device. Or alternatively, you might have non-contact types of measurements, which can be optical, ultrasound, changes of inductance or capacitance in an electrical circle. All of these can be used to measure a position. You might be wanting to measure, say, a mechanical strain, in which case you'd be looking at some kind of resistive sensor, or again, maybe a piezoelectric sensor. If you're measuring magnetic fields, you're interested in things like Hall probes, magnetic flux gates, and more exotic things like superconducting quantum interference devices, or SQUIDs. And we're going to talk later on in another lecture more about optical sensors as part of the spectroscopy series of videos. But under optical sensors, we include things like photodiodes, photoconductors, charge-coupled devices, CCDs, and so we're going to discuss those in more detail later. But the important take-home message to all of these things is that all of these sensors work on physical processes, and in fact, you've actually already got the physics you need in order to understand a lot about how these sensors actually go and work. So what we're going to do is we're going to discuss just a few examples to give you kind of a flavor of some of the ways that things are happening, and to try and draw the connection between some of the physics you've learned in previous years and actually what's going on in experimental techniques. Okay, so I thought I'd start by looking at, say, for example, how a Hall sensor works. So this is stuff that you will have covered with Professor Marrows in last year's Physics 4 solid state lectures, probably. So we start with a square of conductor. And what we're going to do is we're going to apply an electrical current. We'll call IX. And there is a magnetic field which is going to be, call that BZ, which is mu naught times HZ times, so the magnetic field H in amps per meter, giving us a magnetic flux density B. And as a result of this, we're going to measure a voltage Vy across there. And we'll just put a few dimensions on here, so let's just make this width W and this thickness here T. And we'll say we've got charge carriers. So charge Q and a density of them N. Okay, so what's going on here is our current is flowing this way, and then it's going to feel a Lorentz force because of the magnetic field that's running vertically. And that Lorentz force goes as the cross product of the charge on the charge carriers times their velocity and the magnetic flux running vertically. And as a result of that, those charge carriers are going to feel that Lorentz force operating in the y direction, so across the sample like this. And left to their own devices, what would happen is that the charge carriers would accumulate on one side or the other side of this sensor. Of course, that will set up an electric field. So in the steady state, the force on the charge carrier is going to be given by the Lorentz force and the electric field operating in the other direction. So we can write down an equation for that. Which looks like that. The force is just the charge, times then the electric field vector plus the velocity plus the Lorentz force. And strictly speaking, that should be a minus sign, and that should equal 0 in the solid state. Sorry, in the steady state. Okay, so we can go on a bit further with this. So we're going to end up with something that looks like that, but we need to know what the velocity of our charge carriers are. So now we remember that we've got the current, we've got the cross-sectional area, we've got a density, and we've got a charge. And so we can simply write that the current is going to be the number of charge carriers per unit area times the width times the thickness times the charge times the velocity. That's a vector as well. So therefore the velocity is the current over dimensions times the charge. So now we can substitute that in here. We can so we'll cancel out the charge on that expression. It's going to come back in again in just a second. So I cross B over the dimensions times density times the charge. And then we go, but we're not actually measuring the electric field directly, we're measuring a voltage. So the other thing we can see here is that in this geometry, if the current is running the x direction, the magnetic field is in the z direction, the cross product means the electric field must be in the y direction only. So we can say the electric field in the y direction, or the magnitude of it, is the voltage in the y direction over the distance in the y direction is equal to magnitude of the current times the magnitude of the field over all of those things. And now we find that we can cancel out W Ix Bz over Nt Q. Okay, so this is then the Hall voltage of our sensor. Okay, so that's some basic solid state physics, but what do we learn from this? Well, first of all, we learned that our Hall sensor is proportional to the magnetic flux, which is good. It's going to produce a voltage, which is good. And we can work out the sort of estimates of the size of the voltage that our sensor might produce. If we know the current, we know the thickness, we know the number of charge carrier densities. The other thing you can spot is that the voltage you get is going to depend, the sign of the voltage is going to depend on the sign of the charge. So if your Hall sensor has got electrons as its conductor, or if it's got holes, that'll switch the sign of the Hall voltage that you're measuring. It also shows that in order to get this voltage as big as possible, you're going to want to have the N and the T, so in other words, the number of charge carriers per unit volume and the thickness of the thing as small as possible. And so that tells you that a good Hall sensor is something where you can reduce the number of charge carriers, the density of them, and you can make a thin slab. And that tends to take you towards using a semiconductor. So unsurprisingly, Hall sensors tend to be made out of particularly systems called two-dimensional electron gases. And that's where you create a system where you have a sheet of mobile charge carriers in a semiconductor heterostructure that's confined within a very narrow region. And in those sorts of situations, you can actually reduce the number of charge carriers quite substantially as well. And so you can get quite sizable voltages in the Hall voltage. Of course, the disadvantage of that is that these systems tend to have quite a high resistance running in the x direction, which means if you put the current up, the Ix, too much, you end up dissipating a lot of power in your sensor. And that may not be a good idea for other reasons. So this is what I mean by trying to introduce the concepts you've learned in solid state physics into understanding how to design a good sensor. So let's see now if we can use similar ideas to think about how to make a good temperature sensor. So I'm going to start off by discussing how you can use, again, another form of semiconductor technology as a temperature sensor. So we're going to base this on a PN junction or a diode. So we're going to have a PN junction. So we first of all start, always easiest to draw the Fermi energy first. And so we have a conduction band, a valence band, and we have a Fermi energy or electrochemical potential. And you should know from last year's Physics 4 courses that in this situation, we're going to have electrons. Like that. And we're going to have a small number of holes. Like that. And if we just sit here in the steady state, then what happens is the electrons here flow this way, and they're exactly balanced by the electrons up here flowing in the other direction. And likewise with the holes here will tend to go this way, and their exactly flow of them is exactly balanced by the holes going that way. And so overall, there's no net flow of charge carriers. Now, if we look at where these charge carriers are actually coming from, again, you should remember from last year that this is the P side, and that's the N side. In the N side, the reason you have a lot of electrons here is because you have a lot of electrons being excited from donor states, which are just lying in here. And they're promoting their electrons because there's only a short energy distance for them to go up into the conduction band. And likewise on this side, the reason you have a lot of holes down here is because you're receiving a lot of electrons into the acceptor states, which again lie close to the gap, to the energy gap, so the band gap here. These electrons up here are coming from the fact that you have some electrons which are thermally excited all the way from down here to up here. So this voltage here is typically about an electron volt, and if you work it out at room temperature, you have a certain probability you're going to have a number of electrons up there. Likewise, you have a number of holes here, and they're being generated because electrons are being promoted thermally by thermal energy from here up into from the valence band up into the conduction band. So these bits here, the majority carriers are being created by largely by the number of dopants in the system, and the minority carriers here are being created thermally. So now we think what happens if we apply a small, apply voltages to this system. So if we change the bias on this system so that we make the N side come up and the P side go down, okay, so I'm applying a rather severe bias here. So in a position that looks like this, we've had so much bias to this, in fact, we've made the bands go completely level. What's going to happen is you have a huge current flowing for the electrons coming across this way, and much fewer number of electrons going the other direction. Like we can have a huge current of holes flowing this way, and much less in the other direction. So you have a very, very large current flow. But the size of that current flow is determined by the number of electrons here, the number of holes here, and that's determined by the doping. What happens if we apply the other direction of bias? Oops, straight to the right color. Okay, so now we've applied a bias in the other direction, we can draw in the electrons and the holes. That. Now, what's going to happen in this situation is that these electrons here, they can't get across because they're being blocked, because the barrier they've got to get past has got bigger. So there's no electron flow there, but there is an electron flow going in that direction. And likewise, there's no holes going this way because they're being blocked with a bigger barrier, but those holes there are able to move across the junction. Now, why is that interesting? Because these electrons and these holes are being produced by thermal excitation across the energy gap. So the current you're measuring in this device is dependent on the temperature. And so we can summarize that with a, think about the current voltage that you might get. Okay, no voltage, no current. So if I do it for a low temperature and a high temperature, on this side, there's basically no difference. But what happens here is that as I change the temperature, I get a different curve, and on the negative side, the current I measure goes down in relation to the temperature. How much does it go down by? Well, the number of carriers here, number of electrons in the p side, is proportional to e to the minus the energy gap over Boltzmann's constant times the temperature. And the same is true on the other side. And so what you have here is that the amount of current you're going to get is going to be exponentially dependent on the temperature. In other words, that makes this a really good sensor. Okay, great, so that's fine, except for one slight problem. And that is that in this situation, what I've got is I've got a semiconductor, I've got a relatively small number of charge carriers, and therefore this sort of sensor is also going to be susceptible to the Hall effect. So if I try using this as a temperature sensor in a system with a magnetic field, then I'm going to get a Hall voltage as well. And that's going to interfere with my measurement of my temperature. And so as I change the magnetic field, it's going to look like my sample is changing temperature, but it's not really, it's just that I'm picking up a Hall effect. So you need to go and choose the right type of temperature sensor, thinking about more than just how do I measure temperature and how sensitive is it, but the other ways in which it might be needed. The other problem with this sensor is that, okay, it's fine so long as I've got at least some electrons being thermally excited over this energy gap. So there are two limits where it's going to stop working. One is if it gets very, very hot, then I'm going to have lots of electrons being promoted over here, and eventually it's just going to get to the point where I've got too much current flowing through my sensor. On the other hand, if I get very, very cold, then this current goes to zero, and it gets very, very hard in practical terms to actually do a measurement because I get a voltage and I get no current flow. So again, there's a limited working range of this, which is determined by the actual underlying physics of what's going on. So let's look at another couple of types of temperature sensor and discuss how they can be useful. Okay, so again, another type of temperature sensor that's very commonly used is a thermocouple. And again, this uses physics that you've covered in Physics 4. So if we take a wire of material, and we're going to start off simply having, we'll say this is hot, this end, and this is cold at this end. Now, if this is just a bit of metal, then the electrons at this end, at the hot end, are on average moving faster than the electrons at the cold end because they're thermally excited. So what's going to happen is the electrons move faster here than they do here, and so you're going to get a net flow of electrons from the hot end towards the cold end. Now, of course, in the study, eventually you end up with accumulation of electrons here and a deficit here. And so that means you have an electric field, and eventually the electric field is going to counteract the force of from the electric field, is going to counteract the flow of electrons. But that means we're going to end up building a voltage along here. And the size of this voltage, let's call this material A, so VA. So VA is going to be proportional to the change in temperature. And that constant of proportionality is going to be the Seebeck coefficient. And there's going to be other terms in there which are to do with the length of the wire and so on, because it's actually an electric field. But it's going to be proportional to this material constant. And in that material constant, in that Seebeck coefficient, you've got information about things like the density of electrons at the Fermi surface and the Fermi velocity and details of the band structure. So it's different for different materials. So if I now take a second material, let's call this material B, and again, same temperature difference across the whole thing. Electrons are going to move from the hot end towards the cold end, and that's going to build up an electric field. So the voltage on this guy here, VB, is going to be the Seebeck coefficient of material B times the temperature. And now we can't access down the hot, we can't access what's going on at the hot end, but what we can do is measure the voltage across the two ends there. Now the voltage down here has to be, or the potential has to be the same here because these two are joined together. So therefore we're getting a voltage difference up this end, which is the voltage we measure, is simply the voltage at A minus the voltage at B, which is going to be a change in temperature times the difference in the Seebeck coefficients. And the Seebeck coefficients depend on the materials. So again, this is telling us we get a voltage which is proportional to the thing we're trying to measure, the difference in temperature from the cold end to the hot end. And it's going to scale with those Seebeck coefficients. Now, to a first approximation, the Seebeck coefficients are independent of temperature, but of course that's not really true. And they do depend on temperature a bit as well. So what you find is that different combinations of materials have a large difference in Seebeck coefficients in different temperature regimes. And so with a thermocouple, what you do is you choose a different type of thermocouple, which is giving you different material combinations, which are then sensitive to different temperature regimes. And so you pick one type of thermocouple if you're trying to operate up to, say, 1000 degrees C. That's typically what's called a type K thermocouple. And you have a different type of thermocouple if you're going up to over 2000 degrees centigrade. Typically you might use a type C thermocouple there. And likewise, again, if you're trying to measure at cryogenic temperatures, you would pick different thermocouples. The problem is that as you get colder and colder and colder, the Seebeck coefficients both tend to go down to 0. And as a result of that, the difference between them gets smaller, and so the thermocouples get less sensitive. So again, understanding the background physics of why your sensors work help you to pick a sensor that is good for the type of thing you're trying to work with. So just as a final example, we can talk about just a straight resistor type, or we'll talk about different resistor type sensors. So you might remember that in your first year tutorial, where you were talking about a type of sensor which is being used to measure, I think it was around what's device temperatures. And this was a type of sensor that had a resistance that went up exponentially with temperature. And so this is a classic example of a sensor which involves charge carriers conducting through the system but undergoing a series of energy barriers. So what you might, for example, imagine is that you have a material where you have a lattice of different ions. And those ions can be either different oxidation state, so 3+ or 4+, for example. So we could take a material with a lattice of ions, and these are all mainly 3+ ions. Except there's one in the middle there that's in a different oxidation state. And so what can happen in this situation is you go, okay, well, that's a 4+ ion. Now let's imagine that we transfer an electron from this 3+ ion over to the 4+ ion. So then this ion now becomes 3+, and that one becomes 4+. And then sometime later we transfer another electron from here. That becomes a 4+, that becomes a 3+, and so on. And eventually you move the oxidation state along, and you actually transferred some charge. In that case, you transferred the charge this way. Now, each of these steps involves transferring an electron over an energy barrier. And so what you describe it as is you describe it as a series of different energy barriers. So this would be an energy. Actually, let's call it U versus the position of the lattice. And what you're having here is an energy barrier delta U. And so the probability that you get an electron from here to here is going to go as some kind of number of temp frequency times an exponential energy barrier involving delta U. And so the conductivity of this sigma is going to be proportional to e to the minus delta U over kT. As a result of that, you can see therefore that if we think about the resistance, that the resistance is going to be proportional to e to the plus delta U over kT. And therefore that resistance is going to go up and up and up as the sample gets colder and colder and colder. And so we have something which is potentially, if you try and pass a current through it, you have a voltage coming out that's going to get bigger and bigger and bigger as you get colder and colder and colder. The advantage here is that the actual movement of the charge is relatively slow. There are relatively low mobilities. And that also has the effect of reducing the the Hall voltage you might get. So this sort of sensor then works quite well in the magnetic field and is sensitive to low temperatures. Alternatively, if you don't want to do that, you can think about what happens just with a normal metal. And again, in last year's solid state physics module, you will have covered the resistance versus temperature for a metal. And it looks like that. So it's linear, or near enough linear, over quite a broad temperature range. Then there's a region here it goes as temperatures of the fifth, and there's a classic physics question about why it's to the fifth, and then it levels off at some residual resistivity. So if you want to use this as a temperature sensor, then in this regime here, you have a nice linear dependence between the temperature and the resistance. Of course, it falls off and stops working as you get cold because the resistance levels off. But again, it's using the principles that we've used before in order to understand what's going on with the sensor and to pick the right regime in which to make it work. So the take-home message here is that when you look at a sensor, it's always worth trying to understand how the sensor is actually working to do your measurement. And if you understand how the sensor is working, then you're in a much better position to understand what the right type of sensor is, what regime to work it in, and what some of the potential artifacts might be of using it.